Hi everyone, and welcome to another edition of the Data Idols and Data Science Festival Summer School. I'm Jess, and I'm the Community Director at the Data Science Festival and part of the team that helped put the summer school together. So if you're watching live, thank you so much for joining us. In a second in the chat, you will see a link to our Slack channel. Feel free to join that. You can chat with us, you can chat to other attendees, get to know each other, and also ask any questions and help your other attendees as well during the session. If you're watching this on playback, welcome back. And hopefully you're enjoying the summer school and you've had a chance to check out some of the other videos. So before we get started today, just wanted to say a massive thank you to all of our summer school partners. Every single one of these companies has donated time and energy into putting the summer school together. So we're very grateful to every speaker and every company who has spent so much time putting together all these sessions for you guys. We are very appreciative, so thank you very much. So today's session is going to be with our friends over at Depop, who have been great partners for the past few years. And it's going to be with Benjamin and David, and they're going to be covering roots, repercussions, and rectification of bias in NLP transfer learning. So hope you guys enjoy and see you in an event soon. Thanks.
Hi, I'm David. I'm a data scientist at Depop, work within the MarTech team, and I'm here with my co-host, Ben.
Hello, yeah, I'm Ben, and I'm data scientist in the search and ranking team at Depop.
We're going to be talking about the roots, repercussions, and rectification of bias in NLP transfer learning, and we came up with that title just so that I could trip over it in the first minute. So, first of all, just a warning. This presentation might contain artificially generated text and it could be offensive or upsetting, and we definitely don't want to offend or upset. So if you don't want to look at it, don't, please. So yeah, what is bias? So bias is an inclination or prejudice for or against one person or group, especially in a way considered to be unfair. And you can be biased for something or towards something, and you can be biased against something. When you're biased against something, it's known as harm. So what is harm? So harm, allocative harm, harm comes in two types, allocative and associative. Allocative harm is when a system allocates or withholds a certain opportunity or resource. Whereas associative harm is when a system reinforces the subordination of some groups along the lines of identity. It's like amplifying, essentially, the bias, the negative bias. So we've got loads and loads of different sources of bias, and you'll know some of these already. Some of them you won't. They kind of get grouped together by researchers within between sort of data bias and interpretation bias. And I'm just going to take you through a couple of them. If you want to have a look at the rest of the slides after, then please do. Take them home, read about them, do some research, because it's important to know about, well, all of them. So some of them you'll have definitely heard of before. So you'll have heard of, say, reporting bias. It's the idea that actually the frequency about which people are writing about something is not a sort of reflection of what happens in the real world. And a good example of this is within the UK, especially over the last sort of 400 or 500 years, you've generally got the richest people in the country, very few, able to read and write, and therefore able to actually record anything that was happening. So that's an example of reporting bias. We only know what's happened through their words. Because they're the only people, or we've only got recordings of what they said. Then you've got selection bias. So selection bias is sort of errors caused by sampling incorrectly. So maybe you're sampling too many from one group and not enough from another, or it's sort of not as general as you'd like. So you're actually going to be creating models out of this data that are going to be biased. They're going to carry this sampling error within them. Then you've got other examples. So, for example, historical injustice. This is the idea that if something's happened before and it's now sort of, it was some kind of moral wrong, and now we know that was incorrect. We know that was wrong, and that data that was created back in that time is carrying forwards and actually affecting people now. So affecting sort of, the well-being of current, of living people, or people that are going to be using or affected by these models. Then you've got, say, outgroup homogeneity bias, sort of stereotypical bias. So that's seeing outgroup members as more alike than in-group members. An example of this is I'm a Colchester United supporter. I mean, I don't really watch that much football. Please don't, make fun of me. That's my hometown. So me and amongst all of my sort of Colchester United supporting friends, we all kind of get along and we like each other. But we generally look at people that support Ipswich as they're all kind of like the same, and they've made the wrong choice. They're supporting the wrong team. So we don't try and differentiate between them. They're just bad. So we've got a few more types of data bias in here, but I'm going to move on to interpretation bias. So interpretation bias, you've got sort of in-group bias, which is the opposite of the out-group bias. It's like the tendency to treat, sort of give people preferential treatment if they belong to the same group as you. And there are some really interesting studies done on this, in which you get a very completely random group of people, and you just randomly separate them into two different groups. And they actually start acting as and preferring members of their own group, which is mad, because there's very little reason for them to. Then you've got things like confirmation bias. So it's the a tendency to look for information or data that supports your beliefs, desires, or knowledge, or values. Then we have like experimenter's bias, and I know a lot of you will be coming from sort of you'll be doing degrees at the moment, or you've just finished, or maybe you've just come through a boot camp, or maybe you work in the industry already, and you should all be aware of this, and that is experimenter's bias. So it's like the outcome of an experiment tends to be biased towards what you want, because that's generally why you're doing it. You have this idea and you want your idea to be right. So that hypothesis you're trying to prove, and you're trying to disprove all the others, right? And it's actually really easy to do. You really need to be aware of this. And there are loads of really useful tools within research to stop experimental bias being such a problem. That's why we've got p-values and all that kind of thing. But you still need to be aware of it. So yeah, you've got all of these different types of bias, and I'm going to give you an example right now of one. So this is an old riddle. So a father and a son are in a horrible car crash that kills the dad. The son is rushed to hospital, but just as he's about to go under the knife, the surgeon says, "I can't operate. That boy is my son." Now, can you explain this to me? He's the surgeon. And click pause. And you can unpause it. So yeah, it was an old riddle, and then it was used in a study by Boston University, and the majority of respondents didn't actually realize that the doctor could be female, and that study was done over sort of different groups, and that was actually within groups of males, within groups of females, and within groups of sort of self-described feminists. The majority of people couldn't explain or came up with another excuse or potential. The most interesting were those coming from kids, saying like, "Oh, it must be a relationship in which there are two fathers," which is super interesting. But clearly, like, there's bias in the way that we think. So I'm going to give you some more examples of bias within machine learning, within the data science industry. And we're going to start off with machine translation. Now this, again, not as old as that riddle, but this is an old one. And it's occurred when you could use Google Translate to translate between sentences. I mean, you still can, but they're constantly improving their models and, you know, getting better and better and better. But this happened a few years ago. And if you put in the sentence, he is a nurse, she is a doctor, in English, and translated it into Hungarian or Turkish or other languages with non-gendered pronouns, then it would give you this sort of non-gendered version in Hungarian. I don't speak Hungarian, so I'm really sorry. Then when you took this Hungarian sentence and then translated that back into English using the exact same model, the model would produce, she's a nurse, he is a doctor. Despite being given, he is a nurse, she is a doctor in the first place. And it's created this from a sentence that is non-gendered. So clearly you can see that something's wrong here. The model has learnt something that potentially isn't right or is potentially biased. And in this case, there were just more examples. The model had more examples in its corpus of she being near nurse and he being near doctor, and therefore gave this incorrect sentence. I'd like to say that this is no longer the case. Google have changed this, and the Google Translate now suggests two different options when you translate from Hungarian to English. One will be the masculine version and one will be the feminine version. And this research was done in 2017. Then we've got sort of examples within language models and co-reference resolution models. So here we can see that within the co-reference resolution model, you've got scores that show that actually he is more commonly found, more similar to doctor than she is, and he is less similar to nurse than she is. And again, within the language model, so this is a state-of-the-art RNN. You can see that actually if you condition the non-gendered word on the gendered word, you can see that doctor is more likely than to be found given the word he than the word she, and it's less likely given the word nurse is less likely to be found after the word he than she. Which is obviously, again, carrying gender bias here. So here are some examples with word embeddings. Now, word embeddings are a vector representation of a word. They're a useful byproduct of some models, and they're used all the time. I use them a load at Depop, and most recently, sort of like clustering. And here you can see that in the top graph, top chart, you can see that a linear classifier was used in this particular piece of research in 2016 to separate between gender-specific and gender-neutral words. So below the x-axis, you can see gender-specific, and then above the x-axis, you have gender-neutral words. But you can see here, when it's projected on a plane from she to he, actually that certain words are closer to he and certain words are closer to she, that maybe should and maybe shouldn't be there. And I'd argue actually that these are gender specific words and really they shouldn't be there. So closer to she, you have words like dancers, beautiful, pageant, ultrasound. And closer to he, you have beard, journeyman, genius. Why is genius not closer to she? Then you've got within these word embeddings, you can use them to sort of calculate sentences and relations. So this example here is showing this sort of resultant vector when you take away woman from man. It's actually equivalent to the resultant vector from homemaker and computer programmer. And you can see that clearly there's some kind of bias there that shouldn't be there. It's quite reasonable to expect a computer programmer to be either male or female and a homemaker to be male or female. Then we have in the third diagram, the third category, analogies. So again, these are kind of similar. If you look up to the chart above, they're projected on the she-he plane. And these are the most extreme occupations that have been found within this data set. And you can see that blonde is to she as burly as is to he. Vocalist is to she as guitarist is to he. Feminism is to she as conservatism is to he. And again, you can see why this could be problematic if you then use this corpus going forwards, and you weren't aware of the bias within it. So this is probably going to be quite problematic for some, and this is GPT-2's language generation model. So this research was done in 2019, and it showed text continuations from a prompt, and then the model was to generate text from that. So this model was trained on a huge amount of text data gathered from the internet, and it cost a lot of money to train. And you can see from these examples that generally, I mean, I wouldn't want this published. I wouldn't want this, you know, why wouldn't you want to use this content at all? Because it's showing stereotypes, it's showing bias. Then we have a hate speech detection model. This is more recent. This is 2019. And this, or the research was done in 2019. The model was actually quite recent as well. It's a leading CNN. And it was used to flag social media posts as to whether they were offensive or not. And in the paper, the risk of racial bias in hate speech detection, it showed that actually it was the annotator's insensitivity to the differences in dialect that led to a racial bias. And this led to a bias against African Americans and amplified them, potentially amplified them. And in this case, you can see that it definitely amplified the likelihood of tweets being flagged as offensive was 1.5 times for African Americans, which is awful. So all of these models, and the majority of these models, and majority of language models and so on, rely on corpora. And they get their information data and can therefore create representations from the data within that corpus. So I'm going to take you through a few of them. So first of all, we've got book corpus. Now, book corpus was used by Bart, which is Amazon's sort of creation, and newer XLNet. It used sentences extracted from books, extracted from scanned-in books. It had a load of duplicates. It had a load of sort of a load of genres, but they were generally skewed towards romance and fantasy. And there was a lot of 18+ content, which contained terms like alpha male and submissive female. There was also skew towards Christianity in religious representation, and some authors contributed like a ton more books than others to this corpus. And you can see here that, like, straight out just from reading that description, you've got risks of skewed religious representation. Yeah, there are skewed genres. You could have some really problematic stuff coming out of these. And there is, like, definitely the potential for harmful gender stereotypes, especially considering the terms alpha male and submissive female. So then we have another corpus, CC News. So this was used by BERT and the larger models, and it contains news articles from news sites all over the place, all over the world. And this was built up from 2017 to 2019. And within the corpus, like, there are news sources that are very diverse, and you're not really sure what the sort of political leanings are of these news sources are. So there's a potential political skew, and you and I both know, I mean, that when you look at the generally available newspapers in the UK, you can tell the difference between the Daily Mail, the Sun, and newspapers like the Financial Times and the Guardian. And you can kind of see that the stories that they tend to contain are there to make people read more, or it plays on their own sort of fears or insecurities or sort of interests, right? So there's, within those stories, they could, they can be from say, like, there can be stories on beauty pageants, petty crime, but also through to serious crime, in which, like, the newspaper and news source will focus on this serious crime for a long period of time. So there's potential for harmful racial stereotypes, harmful socioeconomic stereotypes as well. Then we've got C4. So this is even bigger. It was a cleaned up version of Common Crawl. It's used by T5 and therefore Pegasus. And it had sort of the content of Common Crawl, but filtered for like naughty words or bad words. And so dirty, naughty, obscene, and otherwise bad words is actually a GitHub repo that you can go to, where you can actually see all of these. Sorry, my dog is bugging me. It also used language detection models, and it used these to filter the documents. So these language detection models obviously aren't perfect, and would see a lot of slang or colloquialisms and actually judge them to not be English. So therefore, it's not going to carry those into the model. So the model might therefore lack sort of minority ethnic English data, and therefore there is a potential for harmful racial stereotypes. Again, this is definitely something we do not want in a model, especially not coming from a corpus that's supposedly clean. That's all right. He grabbed the toy, so I think he's distracted. Yeah, so Wikipedia. Now this is a really important corpus. It's used by so many models. It's got a lot of interesting data in it. And I'm not going to cover all of the potential issues within the Wikipedia dataset. But it basically contains cleaned articles for each language. The datasets are built from a dump of Wikimedia articles, and it's split by language. Again, you've got this issue that we had for C4, where you're automatically recognizing language, and therefore you're going to carry these again, sort of this lack of minority ethnic English, or dialect in other languages. So each document contains the content of one Wikipedia article, and I'm going to focus here on a specific paper that was published very recently. It was only a month or two ago, and that's miscategorized gender, notability, and inequality on Wikipedia. That shows how deep the gender inequality is on this like really commonly used corpus. I'd highly recommend you read it, and it goes into how articles written about famous females, famous women, be it scientists, actors, whatever, were actually more likely to be flagged for deletion than those about their male equivalents, counterparts, which is mad. And if this has been going on for the last 20 years, you can see why the corpus itself will carry these gender inequalities, or could carry these gender inequalities, and is proven to by in this paper. So the next couple of slides, I'm going to give you a sort of do it yourself. You can actually try and see these biases within some of these models. But again, I'm going to have to warn you here that some of the text is automatically generated and from the models, and it clearly isn't something that I believe, or Ben, and not something that we don't think models that create text like this should really be used. But yeah, so if you head to huggingface.co, Hugging Face is a wicked resource for like deep learning text-based models, NLP. And if you select one of their models, so in this case, select BERT base uncased, and then you type a sentence and you can use mask, so the token mask with the square brackets, to let the model know that it needs to generate a token there. And then you click compute. So for this example, I used two gendered names. So we've got Claire, and Claire got a new job as a mask. And the model suggested for me waitress, nurse, teacher, maid, and model. Now, 3 of those are gender neutral words. We'd expect to see gendered words in there. We'd expect to see gender neutral words in there, but maybe not these specific ones. Then we do the same sentence. We substitute Claire for Steve. You can see that Steve got a new job as a mechanic, bartender, waiter, teacher, and salesman. Now, why should Steve have to be a mechanic? Why can he not be a model? Why should Claire have to be a waitress or a nurse when she could want to serve drinks and be a bartender? And you can see that is learned within the model from the corpus. Now the next one, again, it's potentially worse than this. And here I used religion within the sentence. So here I've got Christians are generally masked to other people, and the model here produced or gave us Christians are generally compared, closer, attracted, hostile, or opposed to other people. But if I substitute Christians for Muslims, I get some much worse suggestions. So in this case, it's Muslims are generally inferior to other people or compared to other people, opposed to. And it's like you just can't say that, and we cannot use the output of this model legitimately. It's awful. So you can see I've given you a load of examples of bias and sort of the repercussions of bias within these models. And I'm going to pass you over now to Ben, who's going to cover sort of addressing how to get rid of this bias, how to make sure that your models are more resilient. So Ben.
Thanks, David. You could just go to the next slide, please.
Okay.
Perfect. So for addressing bias, what I've decided to do is to choose the pre-trained attention-based language models. So that's for the task of language generation that you saw previously, where given a prompt input, the model will output generated text that it believes will be the next sequence of words. So attention-based models have actually seen quite a large rise in popularity as they came into popularity in the last 4 years. And this is because they alleviate some of the issues with recurrent neural networks that that preceded them. And they've quite quickly been adopted by academics and industry for their performance. So in our scenario, we're actually going to be looking at the language model variety of these attention models. And it's basically like a high-level view. This is just a very large neural network that takes in input, encodes it into some format, and then has a decoding stage of the neural network, which will then be used for various tasks such as classification, or text generation, or regression even. So in our scenario here, we can see that the input to the autoregressive decoder is the sequence start token, the dog ran, and then the output becomes the dog ran quickly, which is the complete sequence plus the additional word quickly that it believes is most likely to come next given that sequence. Able to, perfect. So this is the kind of the high-level strategy for using these attention-based models, and it's important to understand this for context of what will come later. So as David mentioned, there are a large variety of corpuses such as C4, CC News, Wikipedia, that contain a vast amounts of human-generated text. So the idea of these attention-based models is they actually make use of this huge corpuses that are available. And what they'll generally do is they will have a very, very large neural network, and they will train the model to perform very generic tasks on these corpuses. So for example, they might extract sentences from Wikipedia and then randomly mask certain words inside the sentences. And then the objective of the model will be to predict what those masked words were. And alternatively, it might be sentence classification, where given two sentences together, it predicts whether these sentences preceded each other or not, or came from the same document or not. But the overall goal of these generic tasks is for the model to be able to build a general understanding of what these words mean. So given a word, it sees all of the contexts that these words are used inside of, and then it can build a kind of relational contextual understanding of these words. And generally, the pre-training stage is extremely expensive and very labor intensive, and they're normally done by companies with a large amount of resource. And so these models, once they are pre-trained, they can then be exported and used by other people. And this is where the fine-tuning stage comes in. So this might be that somebody has a very specific NLP task that they want to achieve, and they create their own data set. So for example, they may want to build a spam detection model. And so they build this very highly curated data set where they have the text of the document, and then they have a label that indicates whether this document is spam or not. And so they will fine-tune the model on this curated data set, and the fine-tuning stage will update the weights from the pre-trained state in such a way that the model can now perform incredibly well on this fine-tuning task of detecting spam. And then this will output a final model artifact. Now, the beauty of this strategy is that large corporations can provide a pre-trained model that's taken quite a lot of resource to build, and then release that model, and this model can become available to anybody with like a very low barrier to entry. However, they're able to fine-tune this model on their task and receive Google-like performance on their task. And this is why these models are becoming so popular. So before we get into how we will address bias in these types of models, it's good to kind of go over the more well understood and the I guess these are the more traditional approaches to addressing bias in machine learning. So the first type is actually augmenting the data itself. So this is a kind of an attempt to eliminate the bias from the corpus. And you can see on the right-hand side here, this is a very typical strategy, will be to flip the gendered pronouns inside sentences. So for example, he worked as a doctor at St. Thomas's Hospital, will then go to she worked as a doctor at St. Thomas's Hospital. And similarly, the grandmother was proud of the home-cooked meals she served her husband, will then get flipped to the grandfather was proud of the home-cooked meals he served his wife. Now, the idea behind this strategy is that the negative and positive stereotypes, plus all the other biases that go along with gender, will be equally shared amongst both genders. And as a result, the idea is that the corpus will be less biased towards one way or the other. So the second strategy is actually creating a bias-aware objective function that you jointly train along with your regular loss function during the training phase. So for example, on the right-hand side at the bottom, you can see that the sentence, he is a lifelong bachelor, gets fed into the language model. Now, this is the original sentence from the corpus, but what we do for this bias-aware objective function is we create an alternative version of this sentence that has a counterfactual change. So he is a lifelong bachelor will then get translated into she is a lifelong bachelorette. And what we do is we take the output of the language model for both of these variations, and we feed it into a sentiment classifier. Now, in a model that's completely fair, both of these sentences should receive the same sentiment, whether it's negative or positive. However, as we've observed, there are loads of biases inside these models, and as a result, the sentiment classifier is likely going to deviate between the two sentences. And so the fairness objective function is to actually minimize that variance in the sentiment classifications between these counterfactual sentences. And in a way, this acts as like a regularization to the original objective function. Now, both of these approaches are really popular for NLP. However, there are some issues with their use in our attention-based models. And this is largely down to the fact that these large pre-trained language models, they're trained on really large and varied corpuses, which generally are quite hard to handle and not easily accessible all the time. They're also trained on a large amount of compute resource, which is definitely not accessible to everybody. Typically, your largest companies, Microsoft, Amazon, Facebook, Google, the typical suspects, these are the companies that have the resource to pre-train these language models. However, if you're a smaller company who doesn't want to or can't actually invest this much in retraining a model, then you actually can't debias the model through these strategies. And largely, along with the compute resource, these models are extremely expensive to train because the compute resource is expensive to use. GPT-3 reportedly costs $12 million to train just once, which would definitely hurt the budget of any company out there. It would definitely be a noticeable spike. So what this means is that we can't actually attempt to debias the model at the pre-training phase. We're going to have to try to debias the model after it's been pre-trained. So this takes us to the word embeddings. So David has described briefly what these word embeddings are and how they can actually hold biases inside of them. So our pre-trained language model, because it's a huge neural network, the encoding stage of the network outputs what can effectively be understood as an embedding that can represent the words that have been inputted. And so this is what we're going to be doing. We're going to be doing word embedding manipulations in order to debias the model. So, I mean, you can see here on the right-hand side that this is an example of words that have been projected into a two-dimensional space. And you can very clearly see that there's a geometrical relationship between words that actually makes a lot of sense. So he and himself, that difference in those vectors is the same difference as she and herself. The same is true of Paris to France and London to England and Rome to Italy. So these are all very correct and logically sound relations. However, there are biases that are also captured in this, as David mentioned, such as the difference between man and woman is roughly analogous to the difference between doctor and nurse. Now, this is a relation that is basically unacceptable for any model that will be going into production. And this is the type of information that we need to somehow remove from the bias, from the word embeddings, whilst retaining the useful relations that serve the model to produce correct predictions. So this is a very high-level simplified diagram that shows you the strategy that these attention models use to generate the next word given a word that they've seen. So starting from the left-hand side, we have the input sequence, she works as A, and then blank. And this is fed into the model, which is received by the decoder, and the decoder then outputs something called a context embedding. Now, the context embedding is effectively a word embedding, sorry, a vector representation that represents the entire sequence. So rather than just one word, it represents the entire historical sequence that's been seen in the past. And then a vector multiplication is applied to the word embeddings of each word inside of our vocabulary that's to be considered. And the outputs of these multiplications are scalar values that can be transformed into probabilities on the right-hand side. So you can see in our case, the sequence she works as A, after it's gone through our decoding strategy, then vector multiplication, we can see that the words nurse and stylist are much more probable to the model than the words doctor and architect. So we can visually see here that this model is biased. So for our strategy, we aim to remove the bias from the context embedding that's outputted by the decoder. This is the stage, and this strategy is actually known as iterative null space projection. And there's a link to the paper near the end of the slide if you'd like to read more about this strategy. So the first thing we have to do is we have to create something called a bias subspace. So what we do here is we curate a list of pairs of words that differ from each other in meaning only by gender. And it's very important that we do this. So we have these words on the left-hand side, and these pairs are she, he, her, his, female, male, and we collect the embeddings for these words. Now, it's very important that that they differ in meaning only by gender, and you'll see why later. So what we do is we apply an algorithm known as principal component analysis to these embeddings. And what this process is basically given this large dimensional space in the word embeddings, principal component analysis will try to discover directions inside those embedding spaces that explains or has the most explanatory power to the variance in those embeddings. So because we have chosen words that differ meaning only by gender, this means that the directions will reflect gender differences. So you can see on the right-hand side where PCA has been applied to convert the embedding space of n dimensions into a two-dimensional space. We can see along the y-axis that high values along that direction correlate strongly with words that are female biased. And then on the x-axis, we can see that that direction correlates strongly with words that are biased towards the male space. And in this strategy, in this way, we've created this bias subspace where we can start to understand if words in our vocabulary have some sort of leaning towards one bias, so one gender or the other. So our next strategy then is to identify all the bias-sensitive words that are in our vocabulary. So how we do this is we get each embedding in the vocabulary and we project it onto this bias subspace that we've just created. And in our scenario, we can see that we've collected 6 bias-sensitive words. Tanning, homemaker, and modeling have been shifted towards the female biased area of the space, whereas chief, genius, and captain have moved towards the male area of the bias subspace. And as a result, we're now able to classify whether a word has a bias towards male or female. So because we're able to assign this label to these words, what we've done is, you can see on the left-hand side, we have the embeddings for the bias-sensitive words that we captured previously, and measuring where they existed in that bias subspace, we've attached a label of he or she, depending on where they existed. And what we do is we then train a linear classifier on these embeddings to classify or to predict whether the word is male or female. So it's the objective of this linear classifier is simply to take the embedding as input and classify whether it's male bias or female bias. Now, this is quite ingenious because the what this means is that the classifier waits after it has been trained and has achieved a good performance. The classifier weights actually contain the information that is needed to transform an embedding space into a gender bias subspace. So it's able to understand what particular components of the embedding space are actually contributing towards the gender bias. So you can see on the right-hand side here that the linear classifier is effectively creating a decision boundary that maximally separates the bias-sensitive words. So it's very, so now that we have a linear classifier, we do to our next step. So the next strategy is to create a vector such that if we multiplied the vector by the embedding the word embedding of the input, if we multiplied that embedding by our new vector and then applied it to the linear classifier would be unable to predict whether that word had a male or female bias. So what this is generally known as in the mathematics world is null space projection. So we project the embedding space into the null space of the classifier weights. Now, generally, this is I won't go into detail about how we actually acquire the null space projection vectors, but you can have faith that there exists at least one vector, because the vector of all zeros is a null space projection of all matrices. Now, what this does is actually quite ingenious. So given our null space projection with the vectors, when the classifier weights are applied to this new embedding, the words actually get projected onto the boundary space of the classifier. So in effect, the classifier is no longer able to predict whether a word is biased towards one gender or the other, because it exists on the boundary of the decision boundary. And as a result, the probability is now 50-50. So an example of a null space projection could actually be, like I said, the vector 0, all 0. However, this would be a very destructive null space projection, because if we were to apply all 0 to our embedding vector, then the vector just becomes 0, and then we apply that by the weights and it just becomes 0. And these words end up getting projected to the origin. And as a result, we lose all information, including the most useful information about these words, not just the gender bias. And so we actually have to do a clever function to acquire null space projections that project the word onto the decision boundary in an orthogonal manner. And in this way, we are only extracting the information that is pertinent to predicting gender and nothing else. So this is our null space projection function. And in the literature, this is known as a linear guarding function, in the sense that the discriminatory power for these models, for linear models, has now been destroyed. And you can see here that by applying our null space projection to the context embedding I mentioned previously, we now create this new embedding that retains information that's useful, but has completely and kind of surgically removed the information that might bias the embedding towards one gender or the other. And then we can reinsert that embedding into our pipeline. So now this orange embedding represents the original context embedding being applied to the linear guarding function. And now when we do the matrix multiplication to the embeddings of the rest of our vocabulary, we can see that the probability of all of these various profession embeddings is now equal. So they're all 0.2 because the model has been effectively debiased. So this just represents one strategy for debiasing word embeddings. And I hope it gives you a good intuition that word embeddings are something that retain bias, and it is possible to remove that information. Thank you. This kind of concludes the presentation. And I hope that you leave knowing a lot more about bias and its implications and how to address it in machine learning. Thank you very much.